Irreducible complexity in the context of engineering design. And how this points to intelligent design in the biosphere. The concept of irreducible complexity has sparked significant debate in the realms of biology and philosophy, particularly in relation to intelligent design. However, when considered in the context of engineering design, irreducible complexity becomes an essential and practical principle that is widely recognized. It describes systems that cannot function unless all of their parts are present and properly integrated. In engineering, these systems are carefully designed and constructed to perform specific tasks, where the removal or malfunction of any one part renders the entire system inoperative. Defining irreducible complexity in engineering. Irreducible complexity, as defined by biochemist Michael Behe, refers to a system composed of several interacting components that contribute to the basic function, and the removal of any one of these components results in the system ceasing to function. In engineering design, this principle is not just a theoretical idea but a daily reality faced by engineers. Whether designing mechanical systems, electrical circuits, or software architectures, engineers often create systems where every part plays an indispensable role in the overall functionality. A typical irreducibly complex system is one in which multiple interdependent parts must be present and work together for the system to fulfill its purpose. These systems are distinguished by their inability to be simplified without losing functionality, making them resistant to gradual or piecemeal reduction. In engineering, this leads to a process where each component must be precisely designed and placed to ensure the integrity and operation of the entire system. Examples of irreducible complexity in engineering. Mechanical systems. The internal combustion engine. One of the clearest examples of irreducible complexity in engineering design is the internal combustion engine. An engine is composed of several critical components: pistons, crankshaft, fuel injectors, timing mechanisms, and valves, that must all work together for the engine to function. If any one of these parts is removed or malfunctions, the entire engine will cease to operate. For instance, without properly functioning fuel injectors, the engine cannot deliver the correct amount of fuel to the combustion chamber, resulting in a complete failure to ignite and power the vehicle. Similarly, the timing belt synchronizes the movement of the pistons with the opening and closing of the valves. If the timing belt snaps, the precise coordination needed for combustion is lost, and the engine cannot function. The engine exemplifies irreducible complexity because each part is essential, and no component can be eliminated or dramatically simplified without causing the system to fail entirely. Electrical systems. A circuit breaker. In electrical engineering, a circuit breaker serves as a crucial safety mechanism designed to protect circuits from overload or short circuits. The breaker consists of several interdependent components, including the switch, electromagnet, bimetallic strip, and contacts, all working together to detect dangerous current levels and interrupt the flow of electricity. The removal of any component, whether it is the electromagnet that senses high current or the contacts that physically break the circuit, renders the breaker ineffective. Each part is finely tuned to respond to changes in electrical flow, and none of the components can be dispensed with while retaining the system's protective functionality. In this case, the circuit breaker represents an irreducibly complex system, where each element is indispensable to the overall safety and operation. Software systems. Operating systems. Software development also illustrates the concept of irreducible complexity. Consider an operating system, OS, such as Windows or Linux. An OS is made up of numerous interdependent modules, including memory management, file systems, process scheduling, input, output management, and security protocols. Each of these modules must function correctly and in coordination with the others for the operating system to perform its duties. For example, if the memory management system fails to allocate and deallocate memory properly, other programs may not have the resources they need to run, leading to system crashes. Similarly, without the process scheduling module, the OS cannot handle multiple applications at once, rendering it effectively useless for multitasking environments. Like mechanical and electrical systems, software systems also depend on multiple interdependent components that form a cohesive whole. The removal or failure of any one component breaks the system, making it irreducibly complex. Aerospace engineering. Flight control systems. In the field of aerospace engineering, flight control systems are critical to the safe operation of aircraft. These systems involve several subsystems: hydraulics, avionics, control surfaces, sensors, and feedback mechanisms that must work in precise coordination. The interdependence between these components is essential for maintaining stable and controlled flight. If, for instance, the hydraulic system that operates the control surfaces, like flaps and ailerons, fails, the pilot would lose the ability to maneuver the aircraft. Without proper sensor data, the avionics systems cannot make the necessary adjustments to maintain altitude, speed, or heading. In short, removing or disabling any one of these components renders the entire flight control system non-functional, again demonstrating irreducible complexity in engineering design. Why irreducible complexity is essential in engineering. The presence of irreducibly complex systems in engineering design underscores the importance of foresight, planning, and intelligent assembly. Engineers must consider how each part of a system contributes to the overall function and must design these parts to work together in perfect synchrony. There is no room for random assembly or gradual, unplanned changes in the development of these systems, as the entire design could collapse if even one element is compromised. Necessity of foresight and planning. Engineers working with irreducibly complex systems must account for the precise arrangement of components from the beginning. This means that during the design phase, the engineer must envision the final system and its intended function, planning for every potential failure point and ensuring that all parts work harmoniously. The successful design of such systems demands intelligent input, not trial and error processes. Holistic approach to design. The principle of irreducible complexity drives engineers toward a holistic approach, in which the entire system is considered as an interconnected whole rather than as a collection of independent parts. This requires engineers to think beyond isolated components and recognize the necessity of each part for the overall function. In complex systems, component isolation or modification without regard to the whole can result in total failure, reinforcing the idea that irreducibly complex systems must be approached as cohesive units. Limitations of incremental changes. In both biology and engineering, incremental changes, the gradual modification of one component while others remain unchanged, are often insufficient to improve a system. An irreducibly complex system cannot evolve by small, step-by-step modifications because intermediate stages would be non-functional. This is particularly clear in engineering systems like engines or electrical circuits, where the removal or simplification of a part results in complete system failure. For instance, removing the camshaft from an internal combustion engine and gradually replacing it with random components would not produce a better engine, but a non-functional one. Similarly, attempting to modify the key components of a flight control system without regard to how these parts interact with the rest of the system would result in catastrophic failure. Lessons from engineering for other fields. The concept of irreducible complexity in engineering offers important insights for broader discussions about complexity in nature and the origins of complex biological systems. Engineers recognize that irreducible complexity is a natural and unavoidable feature of systems that are designed with a specific function in mind. Whether we are dealing with machines, circuits, or software, irreducible complexity demands intelligent design, planning, and careful assembly. Similarly, in biology, the existence of irreducibly complex systems, such as molecular machines like the bacterial flagellum or cellular processes, points to the involvement of a designer rather than the result of random, unguided natural processes. Just as in engineering, where no complex system can arise spontaneously or through incremental, unplanned changes, biological systems that exhibit irreducible complexity suggest the hand of an intelligent creator. Conclusion. In the context of engineering design, irreducible complexity is not a theoretical or controversial idea. It is a well-established principle that engineers encounter regularly. Systems in fields ranging from mechanical and electrical engineering to software development and aerospace design demonstrate the necessity of multiple interdependent parts functioning together in harmony. These systems cannot be reduced without losing their functionality, and their successful operation depends on intelligent planning and design. Therefore, rejecting the concept of irreducible complexity in other domains, such as biology, is irrational. The same principles that govern the design and operation of complex systems in engineering apply to the natural world. Both require foresight, planning, and intelligent design to account for the intricate arrangement of parts that work together to achieve a specific purpose. In this light, irreducible complexity serves as a powerful argument not only for engineering design but also for the broader notion of intelligent design in nature. Thanks for watching. Please like, share and subscribe, and comment below if you agree or would like to add your thoughts. If you would like me to respond to your comment, please make a level 1 comment directly below the video. I will respond to all polite level 1 comments even if it takes me a while, due to other commitments.